There is a moment, most people have experienced it without ever stopping to think about what it actually is, where you walk into a room that has just been emptied of furniture, and before you even see the bare walls, before your eyes have a chance to register the stripped down space, your voice tells you. You say something ordinary, your name, maybe, or just a short sentence to whoever else is there, and the sound comes back differently. Not just louder. Different in a way that feels almost personal. Like the room is handing something back to you that you didn't know you'd given it. And you think, oh, this room sounds empty. As if the room has a voice of its own. As if it remembers things. It does, in a way. Not in any mystical sense, not in the soft poetic sense people reach for when they want to say something sounds profound. In a genuine, mechanical, measurable, physical sense, a room that you have lived in for years carries the acoustic signature of every object that has ever sat inside it. When you remove those objects, the room says so. The physics of that, the actual mechanics of how a wave of compressed air manages to encode, transmit, and reflect the precise geometry and material properties of a space, is one of those things that sits at the edge of the invisible and, once you understand it, never quite lets you look at silence the same way again. Let's start at the beginning, which is not where most people think the beginning is. Sound is not primarily a wave in the way we draw it on paper, that smooth sinusoidal curve, that elegant oscillation. That's a useful mathematical description, but it can give the impression that sound travels as a ribbon, a neat undulation moving through space. What's actually happening is far more chaotic and, once you picture it correctly, far more interesting. Sound is a pressure event. When something vibrates, a vocal cord, a guitar string, a hand clapping, it shoves the air molecules adjacent to it, compressing them into a slightly denser cluster than they were before. That cluster immediately pushes against the next cluster of molecules, which pushes against the next, which pushes against the next, and that cascading compression propagates outward in every direction simultaneously, like an expanding sphere of disturbance. Behind that compression, as the original vibrating object pulls back, it leaves a region of slightly lower pressure, a rarefaction, and those two events, the compression and the rarefaction, alternate at the frequency of the original vibration. That alternating pulse, that rhythm of push and pull, is what we call sound. In open air, over a flat field on a still day, this sphere expands outward and eventually dissipates. The energy spreads across an increasingly large surface area, and, according to something called the inverse square law, the intensity of the sound drops in proportion to the square of the distance from the source. Double the distance, and the intensity falls to 1/4. Triple it, and it falls to 1/9. This is why sound fades when you walk away from its source. The energy isn't disappearing, it's diluting, spreading thinner across larger and larger shells of space, until it's indistinguishable from the background thermal jitter of the air molecules themselves. In open space, that's roughly the end of the story. But put a room around that sound, and something entirely different begins. A room is, in the language of acoustics, a bounded medium. Instead of that sphere of pressure having room to expand indefinitely and dissipate harmlessly, it hits a wall, and here is where it gets genuinely interesting, because what happens at that wall is not simply that the sound stops or bounces back perfectly the way a rubber ball might bounce off a concrete floor. What happens is far more nuanced, and it depends on something most people have never thought about: the acoustic impedance of the material. Impedance, in this context, is essentially a measure of how resistant a material is to being pushed into motion by a pressure wave. Air has a certain impedance. Concrete has a vastly different impedance. Wood has another. Soft furnishings, a sofa, a curtain, a carpet, have impedances that place them in a very different category from hard surfaces. And when a sound wave traveling through air strikes a surface with a different impedance, three things happen simultaneously in proportions that depend on that impedance mismatch. Some of the wave's energy is reflected back into the room. Some is transmitted into the wall material and propagates through it, which is why you can hear your neighbors through a wall, though attenuated, and some is absorbed, converted not into reflection or transmission, but into heat. A microscopic, almost absurdly tiny amount of heat, but heat nonetheless. The mechanical energy of the pressure wave is converted into the random thermal motion of the molecules in the wall material. Sound becoming warmth. That is not a metaphor. That is literally the physics. The ratio of how much energy is reflected versus absorbed depends entirely on the material. A bare concrete wall might reflect 98 or 99% of the incident sound energy. It absorbs almost nothing. A heavy curtain, by contrast, might absorb 60 or 70% of the sound across the middle and high frequency range. The fibers of the curtain, all those tiny, irregularly arranged threads, act as a kind of mechanical labyrinth through which the pressure wave must travel, and at each twist and compression, a tiny fraction of the energy is converted into heat through viscous friction between the fibers and the air trapped between them. This is why soft objects in a room change the way it sounds. It is not abstract. It is molecular scale friction transforming one form of energy into another. Now put all of this together in a real room. A sound is made, say, someone speaks. That initial pressure wave expands outward in all directions. Some of it reaches your ears directly. That's the direct sound, the first thing you hear, the sound that arrives with no reflections, carrying the pure signal of the source. But simultaneously, the rest of the wave is hitting every surface it can reach. The floor, the ceiling, the four walls, and every object in the room. Every one of those surfaces reflects the wave back, and each reflected wave now travels toward every other surface, bouncing again, each time losing a small percentage of its energy to absorption, until eventually there is not enough energy left to compress the air molecules above the threshold of hearing, and the sound dies. The total time from when the initial sound stops to when the reflected energy falls below that threshold is called the reverberation time, and it is typically expressed as RT60, the time it takes for the sound level to drop by 60 decibels from its peak. In a very live, hard-surfaced room like a stone cathedral, this can be 4 or 5 or even 8 seconds. In a recording studio designed for acoustic clarity, it might be less than a quarter of a second. In an anechoic chamber, a room lined with thick wedge-shaped foam that absorbs almost all incident sound, it can be so close to zero that people who sit in one for extended periods report disorientation, even hallucinations, because the brain is not built for a world where sound does not return from the environment. That is worth pausing on. The absence of echo is not silence. It is something stranger and more unsettling, which tells you something important about the role that reflected sound plays in our basic sense of being located in a physical world. We use the return of sound, unconsciously, continuously, to understand where we are, not just in the crude navigational sense of echolocation, which we tend to attribute to bats and leave there. Every moment of every day, The way sound bounces back to your ears from the walls around you is being processed by your auditory cortex and used to build a model of the space you occupy. This is not a secondary or marginal function of hearing. It is central to it, and it operates entirely below conscious awareness. You walk into a room, and within milliseconds, long before any deliberate analysis, your brain has extracted from the reflections an estimate of the room's volume, the approximate distance to the nearest hard surfaces, and the material properties of those surfaces. You didn't decide to calculate any of that. The auditory system just did it quietly, using the physics of reflected pressure waves, the way it always does. Now here is where the memory of the room enters, not as metaphor, but as mechanism. Every object in a room has an absorption coefficient that varies with frequency. This is the key detail. A heavy curtain might absorb 70% of sound at 2000 Hz, but only 20% at 100 Hz. A wooden bookshelf absorbs sound differently depending on whether the shelves are filled with books or empty. The books, those compressed, irregularly stacked slabs of dense material, absorb and scatter the mid-range frequencies quite efficiently. The empty shelves reflect them. A sofa absorbs high frequencies in its fabric, but reflects some low frequencies from its hard wooden frame. Every object, in other words, is not just an absorber or a reflector in some uniform, frequency-independent way. It is a frequency-selective filter. It acts differentially on sound, depending on the wavelength of the pressure wave, and the wavelength is inversely related to the frequency. High frequencies have short wavelengths of a few centimeters, and low frequencies have long wavelengths of several meters or more. This means the reverberant field inside a room, that rich, multi-reflected soup of sound that fills the space whenever any noise is made, is shaped in its frequency content by every object present. The room's objects collectively determine which frequencies are damped quickly and which linger. This is what gives rooms their characteristic acoustic signature. A furnished living room and the same living room emptied of furniture are, from the perspective of a sound wave, fundamentally different physical environments. The furniture was absorbing energy at specific frequencies, breaking up reflections from the walls, scattering coherent wave fronts into diffuse clouds of shorter, less resonant bounces. Remove it, and the raw geometry of the room takes over. The walls, floor, and ceiling define a set of resonant frequencies, called room modes, at which the reflected waves reinforce rather than cancel each other, building up standing waves at specific pitches. These are the frequencies at which the room itself wants to vibrate, and they are determined purely by the dimensions of the space. For a rectangular room, the fundamental modes occur at frequencies whose half wavelengths are exact integer multiples of the room's length, width, or height. A room with a length of 5 meters, for instance, will have a strong room mode at approximately 34 Hz, because 34 Hz has a wavelength of about 10 meters, and its half wavelength is 5 meters, which fits exactly into the room's length with a pressure maximum at each end. This mode doesn't disappear when you furnish the room. It's still there, still a mathematical consequence of the geometry. But the furniture damps it. The soft surfaces absorb energy at that frequency. The irregular shapes scatter the wave fronts, preventing the clean standing wave from fully establishing itself. Without furniture, that mode rings clearly. The room booms at frequencies it prefers. You can feel this when you speak in an empty room. Certain vowel sounds seem to resonate more than others, as if the room is selectively amplifying specific pitches. It is doing exactly that. It is expressing its preferred frequencies, the ones encoded in its dimensions, no longer suppressed by the objects that used to live there. This is what it means for a room to sound empty. It is not simply that there is less absorption, though there is. It is that the room's own resonant character is now dominant, unfiltered by the furniture that was moderating it. The room is, in a sense, expressing itself without the objects that used to modify its expression. And when you remove those objects and hear that distinctive change in acoustic quality, you are not imagining something. You are perceiving a real physical phenomenon. The sound of the room genuinely has changed because the boundary conditions for the wave equation governing sound propagation in that space have changed. Less absorption at specific frequencies, different scattering characteristics, a longer reverberation time, a different modal structure dominating the reverberant field. These are quantifiable, measurable differences. Acousticians can walk into a room and, by firing a pistol or a starter gun and measuring the decay of the sound with a microphone, extract the RT60 at multiple frequency bands and reconstruct a fairly detailed picture of the room's contents. The sound knows what's in the room. The decay curve carries that information. But it goes even further than furniture. A room that has had people in it for a long time sounds slightly different, in ways that are genuinely measurable from an identical room that has never been occupied. Human bodies are excellent sound absorbers, particularly at mid and high frequencies. A room full of people at a concert or a lecture sounds very different from the same room empty. This is something concert hall acousticians have to design for explicitly. They use upholstered seats that absorb, roughly, the same amount of sound as an occupied seat, so that the acoustic character of the hall doesn't dramatically shift as it fills with people. And even more subtly, the everyday presence of objects, paintings on walls, rugs, books on shelves, the irregular surfaces of different furniture, arranged differently, creates a particular diffusion pattern, a particular scattering fingerprint, that shapes every sound made in that space. There is a technique in forensic acoustics, an audio analysis, sometimes called room acoustic fingerprinting. The principle is that any recording made inside a specific room will carry the acoustic signature of that room embedded in its reverberant tail. The way reflections follow the direct sound, the specific frequency content of those reflections, the decay curve. If you know what the room's acoustic signature is, you can compare it to a recording and determine with reasonable confidence whether that recording was made in that room. The room leaves its mark on every sound that passes through it. The physics of the reflections encode the geometry, the material properties, the contents of the space into the pressure field that eventually reaches your ears or a microphone. Sound carries the room with it. Think about what this actually implies. Every recording ever made carries, embedded in its reverberant structure, a kind of acoustic portrait of the space in which it was recorded. A recording made in a certain apartment, in a certain city, in a certain decade, carries the acoustic signature of that apartment, its dimensions, its surfaces, the furniture and objects that were in it at the time of recording. Those objects have since been moved, replaced, or destroyed. That apartment may no longer exist, but its acoustic signature persists in the audio file. The room's memory is in the sound, not as a ghost, as a physical record, as the mathematical consequence of boundary conditions and wave equations that were operative in that moment and no other. And now there is something stranger still to consider, and it requires you to sit with the physics a little longer before the strangeness becomes clear. When you are inside a room, the sound you hear at any moment is not just the direct sound from the source. It is a superposition, a mathematical sum, of the direct sound and every reflection that has arrived since the sound began. Those reflections arrived at different times, from different directions, having bounced off different surfaces and objects. Each one carries a slightly different spectral signature, depending on which surfaces it contacted, how many times, and how much energy was absorbed at each frequency. The signal arriving at your ears is the integral of all of that history. All of the paths that sound has taken through the room, all of the surfaces it has struck, all of the absorption that has occurred, all of it is summed, every moment, into the single pressure variation at your eardrum. You are, at every instant you are inside a room, receiving a report on every surface in that room. The room is describing itself to you in the only language it has. This is not a small observation. It means that the act of hearing, any act of hearing in any enclosed space, is an act of acoustic exploration of that space. You are not merely receiving a signal from a source. You are receiving a signal that has been processed, filtered, reflected, absorbed, and scattered by everything in the environment between the source and your ears. The reverberant field is not noise or interference to be removed from the signal. It is information. It is the room's report on its own geometry and contents, transmitted in the medium of the pressure variations that carry it. Your auditory system evolved to read that report. You do it automatically, every moment, without being aware of it, extracting from the reverberant structure a continuous, real, time map of the acoustic environment. There is a mathematical description of this process called the room impulse response. If you were to fire a single, perfect, instantaneous pulse of sound into a room, a theoretically perfect Dirac delta function, a single spike of pressure lasting for zero time, and you measured the resulting pressure variations at a microphone in the room over the following seconds, what you would record is a complex decaying signal that encodes the entire acoustic character of that room. That signal, the room impulse response, contains within it the direct path from the source to the microphone, followed by the first-order reflections, saw the sound that bounced off exactly one surface before arriving, then the second-order reflections, then the third, and so on, each set arriving slightly later, each slightly attenuated. The density of reflections growing rapidly until the signal becomes what acousticians call the diffuse reverberant field. A dense, essentially random superposition of reflections from every direction, and then gradually dying away as the energy is consumed by absorption. That impulse response is a complete physical description of the room. Given the room impulse response, a physicist could in principle reconstruct the room, its dimensions, its surface materials, the approximate positions and acoustic properties of any major objects inside it. The room impulse response is the room's fingerprint, its signature, its complete acoustic autobiography. Convolution with that impulse response is how audio engineers add rooms to sounds. When you hear a recording where a string quartet sounds like they are playing in a cathedral, the cathedral may have been added digitally by convolving the dry recording with the impulse response of an actual cathedral, captured by firing a starter pistol in the space and recording the decay. What you hear is the acoustic portrait of that specific building, a physical structure that may be thousands of miles away or may have been recorded years ago, instantiated in the audio signal as a mathematical description of its reflections. The room travels with the sound. The sound carries the room's memory across any distance, any interval of time. Now stand in an empty room. Your old apartment, your childhood bedroom, a space you know well that has been stripped of its contents. You speak, you hear the difference. And now you understand, at least partially, what you are hearing. You are hearing the room without its furniture's frequency. Selective absorption. You are hearing the room modes, those standing waves encoded in the dimensions of the space, expressing themselves more clearly than they could when the furnishings were damping and scattering them. You are hearing a longer reverberation time because the walls now reflect more of the energy that reaches them, and the energy bounces back and forth more times before dying away. You are hearing the geometry itself. The bare room is telling you its own shape. The sound is carrying that shape to your ears, the way it always has, only now there is nothing to interfere with the signal. The room is speaking, and what it is saying is, "This is what I am," underneath everything else. And perhaps there is a quality of emptiness that we tend to think of as an emotional or psychological experience. An empty room feels different from a full one. We attribute that to memory, to association, to the absence of familiar objects. All of that is real. But woven into it, inseparable from it, is something purely physical. The acoustic character of the room has changed. The pressure waves bouncing from wall to wall, reaching your ears with a different frequency content, a different decay time, a different resonant quality. These are landing on your auditory cortex and being processed below conscious awareness as spatial information. The room is acoustically different. And that acoustic difference, translated by an auditory system that evolved to extract meaning from the geometry of spaces, registers as something. It registers as a kind of strangeness, a kind of exposure, as if the room, freed of its contents, is saying something it couldn't say before, which it is. It always was. You just couldn't hear it through all the furniture. The physics of echoes is not a complicated subject once you see it clearly. Sound is pressure. Pressure reflects. Reflection encodes geometry. Geometry is the room. You hear the room in every sound it contains. You always have. The empty room is just the room speaking at full volume, in a frequency the furnishings used to muffle. The low, resonant, honest voice of a space that has been stripped of everything except itself. What returns to your ears when you speak in that bare space is not just sound. It is the room handing back its own shape, translated into air pressure, delivered to the only instrument sensitive enough to receive it, which has always been you.